Okay, again. It was, excuse me, system of non-homogeneous equations. And we should know what this means. You just write these things out as columns, and you get a system of equations. You have the G of t thing. It would be a homogeneous equation if it wasn't for that. Okay, so we're going to let psi of t be a solution to the homogeneous equation. The matrix solution consists of columns, and each column represents a fundamental, a member of the fundamental set. And we've been over that, so we should understand that. The fundamental set, well, I just say fundamental set forms the columns of psi. So psi prime equals p of t psi. That's what it means for this thing to be the solution of the homogeneous equation.
So this is it actually a fundamental set in the psi matrix, or is it one member of the fundamental set?
We haven't yet talked about it. We will. Your fundamental set is not unique. It's like a linearly independent set. Oh, you can take all kinds of combinations of those linearly independent vectors and get a new set of linearly independent vectors that span the solution space. Okay? And you know, and there's a simple matrix that connects them, and that's kind of intuitively obvious if you got a good command of linear algebra. But right now, a year removed from linear algebra, probably not as obvious as it ought to be. But we'll make it obvious when we clean up some details. Okay. So anyhow. Any fundamental set going to be a set of vectors, right? Because these things are vectors, n-dimensional vectors if you've got n equations and n unknowns, right? So you get a fundamental set of those vectors. Remember, that's a fundamental set if the Wronskian is non-zero, and the Wronskian is just a determinant of your psi matrix in this case. Okay. Okay, so anyhow, that's your psi matrix. That's an important idea. It's a square matrix. Anyhow, our premise then, that's very similar to premises we've made before, is we've got a solution, a general solution to the homogeneous equation. We multiply that by some vector. Now this, of course, is a function of t, because dy is a function of t. Some vector that's also a function of t. And we magically get a solution to the non-homogeneous equation. In other words, this is going to allow us to accommodate g of t. Okay, so there's our premise. Now, once we have the premise, which makes sense if you think about it enough, especially if you solve a few problems, think about what's going on, but it's very similar to the premise we use for reduction of order or for deriving the variation of parameters, which is what we're doing here, for a single higher order equation. Okay? Okay, so very simple premise, but it's always a little bit tricky. What we expect, if we remember what goes on in those cases, is when we substitute this in here, there's going to be a lot of stuff that just goes away. And we're going to be left with something that allows us to determine u of t, probably by integrating something related to g of t. Okay? That's what we sort of expect. So, and I could make a note here. Once we make this premise, we're going to end up with a variation of parameters. Okay? Okay, so what we do is, first of all, we plug this in here. I want to give this a name. That's going to be our particular solution. Okay? So, now that I've given it a name, I can write it right, its derivative.
So in 11.2, we will not be using C's, we will be using T's, because again, C's.
This product rule, it's this. And we know that the product rule and all the derivatives work for matrices just as well as they do for functions of single variable. Easy to prove, just write it out. Okay? So what do we get? We get
Divided by S over n, right? We don't use, in other words, a standard deviation. We use a standard error of mean because we're dealing
and
with x bars instead of x's, correct? X bars instead of x. Now, there are.
okay, now the matrix product P of t times psi, and then you multiply that by the column vector u.
And I think I haven't tried it, but I think I calculated this with two data sets. But we really don't have to
Okay.
do that. We don't have to do that. Your hypotheses are going to look like this.
Now,
Again, we'll have a null,
knowing that psi
have 4.
is
Again, what we're looking at is situations where we're trying to figure out, is there a
solution
difference
to the homogeneous
in
equation.
these means, all right?
Well, do we see the homogeneous equation
Just a mu.
represented anywhere in here?
So